Very well. So we stated the atom isomorphism theorem, and we now want to we now want to prove it using as few assumptions on H as possible. By the way, does everyone understand what the theorem says? Again, to simplify, let's assume that X is a polyhedron. Although there's a CW proof which is more or less the same. Well, if X is a discrete space, then we well, let's look again at what we're trying to prove. Well, if X is a discrete space, then basically we get both on the left and on the right we get a just disjoint union of more precisely, on the level of spaces we have a disjoint union here and here. So for cohomology we get the direct product, and this is it. The direct product of isomorphisms is an isomorphism. Then we prove the theorem for finite dimensional polyhedra using induction on dimension. And well, actually, there's let me think. No. Let's prove a more general statement, which is that better suited for induction. So we yes we. Okay, so we prove a more general relative version of the theorem. Namely, we want to prove that for every subpolyhedron Y, the map dE comma dE restricted to Y cub SE which I'll explain in a minute. We want to show that for every subpolyhedron, the map which is written here is an isomorphism. If Y is empty, we get back the original map from the Thom isomorphism theorem. Now, what does this does everyone understand what this map is, or should I explain it? Okay, so this thing is the same as the cohomology of dE comma dE restricted to Y. Well, this is clear. Okay, so the Thom class U is in HR of dE comma SE. What happens if we multiply two relative cohomology classes? Well, we get something in the cohomology of the big space modulo the union of the things we have. We take the cohomology mod of, which is why we get this this union here. Okay, so we want to show that this this map is an isomorphism. And again, we start with the case when x is discrete, in which case the both sides will be just either the products of things which are either both 0 when we have a point which is inside y, or they're non-zero, but the map is an isomorphism by our assumptions. Now, now we want to do induction on the dimension of x, and the induction step would be well, the induction step would be to add the n faces for well, for some n now, well, the n faces may intersect, so we want to rule this out. So we okay, let me let me think a little. Okay, so the n skeleton is the n-1 skeleton union disjoint union of disks. I just take a small disk for in the middle of each n cell, such that the disks do not intersect. X prime is homotype equivalent to x prime n is homotype equivalent to x prime n minus 1 is homotype equivalent to x n minus 1. Does this make sense? These are the skeleton. Well, xn minus 1 prime is well, the n minus 1 skeleton plus a small part of each n cell, which such that when we take the union with the corresponding disks, we get everything. So the idea is we have D and we take the n minus 1 prime to be something which is homotype equivalent, but we to the n minus 1 skeleton, but such that we have this. Okay, so well, let's observe that each n cell either is either entirely contained in Y or it isn't. And so the if we take here if we take here everything and replace those with intersected with Y, So we take this thing and we consider it for x and minus 1 and for x and minus 1 prime. My claim is they are exactly the same. Sorry, x n minus 1. Well, what else do we? What else do we need for to do the induction? Let me think a little. I don't want to use the Maigiaturis, which would make things easier. Let's see if there is a way to get around it. Okay, so okay, let's assume, moreover, that the intersection is has dimension n minus 1. So here we have okay, x n minus 1 prime. Here we have d. In which case we could take the long, we want to compare two long exact sequences. Firstly, we want to compare the long exact sequence of the couple f y intersected with xn, y intersected with xn minus 1 prime. And secondly, we well, we want to consider the long exact sequence of the basically, we want to consider the long exact sequence of this restricted to let me write it. Let me write it like this. We let me think. Let me look at everything and think how to make it comprehensible, because so far my suspicion is it isn't. Так, Алексей, понятно ли хотя бы что-нибудь? Well, the general idea is to consider two sequences, two long exact sequences, which are mapped into another by coupling with the Tom clause. The thing is, if I try to denote everything, then it becomes impossible. Let me see if there is a way to make it more. Okay. So yes. Let me. Let me try to write everything in a slightly different way, so as to make it comprehensible. This is what we want to. This is what we want to prove to be an isomorphism. So we compare three things. Firstly, we take the left-hand side and the right-hand side, and we except we intersect everything with x and -1 prime instead of x. Андрей, понятно ли, что происходит? Well, then we have, we can do the same for xn, and now we need to do the relative relative version, meaning we replace everywhere the well, what does it mean to do the relative version of this? Well, this means I replace, okay, so I replace x with xn and y with y intersected x n minus 1 prime. Okay. And what's the relative version of this? Well, I take dE over xn, and then I modulo dE x n minus 1 prime union y union s e restricted to x restricted to xn. Basically, as long as one tries to keep track of the n's, it becomes ugly. But the idea is very simple. Well, because we want everything that happens over y to be modded out, and same for everything which is over x n minus 1 prime. And we mod out this spherization over the whole thing. Well, the first one is easier than it looks like. Either suppose we have a cell. Either it is in y, in which case we just have 0, or it's not in y, in which case we just have the cohomology of a small disk mod the boundary. Вообще, наверное, лучше через, то есть это какое-то убийство. Значит, наверное, лучше через Майера Виториса все-таки, да? Ну, то есть, по сути, это одно и то же, но, значит, выглядит довольно устрашающе. верхнее это, да, значит, ну, то есть верхнее это прямое произведение сфер и нулей. В зависимости от того, лежит клетка в Y или не лежит. Значит, ну, а нижнее это тоже прямое произведение, но значит, фактически того, что сверху, но значит, умножить на значит, стеговое множество диск, который нарисован желтым. So we where these well, the first group is just a product of spheres or zeros, and the second one is a product of either the cohomology of dn cross d Sn stop okay. So both sides, if one deciphers the ingredients, both sides are direct products. And the first one is just the I'm sorry. No. This I think this is red. So the first one is the direct product of dn mod Sn minus 1, and the second one is well, we take the n disk, which is the yellow triangle here. Take the preimage, and we but we need to quotient out everything that happens on the boundary, because the boundary is inside x n minus 1. And we get this. Now, for s n minus 1, we have the statement because s n minus 1 has dimension 1 less. For dn, we have the statement because dn is contractible. And so we by induction hypothesis, we have an isomorphism both here and in the relative case. It's sort of much more, it looks much more complicated than it really is. То есть еще раз, что происходит? Мы прибавляем все, значит, все мерные клетки. Ну, прибавили. Значит, дальше значит, берем объединение двух вещей. Того, что закрашено красным, того, что закрашено желтым. Ну, замечательно. Для красного по индукции считаем, что отображение изоморфизм. Во-первых, оно имеет место, во-вторых, оно изоморфизм. Значит, теперь значит, мы смотрим на относительные гомологии. Там всего по модулю красного. Это то же самое, что желтого по модулю границы, по вырезанию. Значит, но значит, желтый по модулю границы — это значит, диск по модулю сферы много-много раз. Значит, соответственно, значит, что происходит значит, для каждого диска, значит, который закрашен желтым. Значит, либо у нас изоморфизм, значит, два случая. Там клетка принадлежит Y, клетка не принадлежит Y. Если клетка принадлежит Y, то у нас отображение из 0 в 0, оно изоморфизм. Если клетка не принадлежит Y, то у нас значит, на границе значит, мы хотим относительно значит, желтое по модулю границы. Значит, мы берем вот, значит, точно такую же последовательность стройки, но значит, более простую для сферы и, то есть для шара и сферы взяли. Значит, для сферы мы имеем изоморфизм, потому что сфера на размер S1 меньше. Для шара мы имеем изоморфизм, то есть шар геометрически эквивалентен точке. Значит, для относительной гомологии каждого желтенького диска по модулю его границы, значит, у нас изоморфизм. А значит, там в общем случае, когда мы приклеиваем все диски, у нас появляется просто прямое произведение. Алексей, имеет ли это хоть малейший смысл? Андрей. То есть идея в том, что мы значит, шаг за шагом прибавляем клетки все больше и больше размера, если ничего больше не происходит. Jipping, does any of this make any sense? I've just I've just explained the following thing. By induction hypothesis, the map marked asterisk is an isomorphism for x prime and minus 1, and we look at the relative cohomology. The relative cohomology for one long exact sequence is just this, and for the other one is this. And we want to well, first we observe that both sides of both the source and the target of the map are disjoint direct products, and we look at what happens for each factor individually. Well, if we have a cell which is painted yellow in this picture, if the cell belongs to Y, then everything is zero, both the source and the target. If the cell is not in Y, we basically have some bundle over an n-disk, and we want to prove the relative Tom isomorphism theorem when the subcomplex Y is the sphere which is the boundary of the n-disk. Very well. So we basically look at this, but we take x equal dn, y equal Sn minus 1. And for Sn minus 1, we have the statement by induction hypothesis, and for dn, we have the statement because dn is contractible. Let me think. Yes, so we have basically when I talk about dn, I take just the trivial bundle over the n-disk, and the so y is empty, and basically the target of the map would be just the usual Tom space, which is the disk bundle mod the sphere bundle. Okay, so the idea is clear, but the details. Well, I was unable to. I didn't think it through very well. So as a result, we instead of a simple proof, there's a crocodile. Okay, but we're not actually done yet, because this thing only gives us the theorem for finite dimensional spaces. Let me briefly explain how to pass from finite dimensional spaces to infinite dimensional spaces. So the homology commutes with direct products, but the cohomology doesn't. If I take Hom, well, Hom transforms on the level of groups. Hom transforms the direction of all maps. So instead of a direct limit of h xn's, we have the inverse limit. And we have a map from h of x to h of every xn. This is not surprising. And so we have a map into the inverse limit. Again, not surprising. Unfortunately, this map is not always an isomorphism. But the kernel is, well, sort of comprehensible. Meaning the kernel is lim1 of the homology groups of degree 1 less. And the same for the relative homology. So here we assume that we have a directed family of CW inclusions. What does this mean? Well, this means well, suppose y is a subcomplex, then we have the same exact sequence. the same exact sequence, but for relative relative homology. And well, using this and the fact that both lim0 and lim1 are functors, we get what we're after for arbitrary polyhedra, not necessarily finite dimensional. Well, lim1 is the first and the only, only derived functor of the lim functor for well, at least for abelian groups. Then, if we have a more complicated abelian category, then there may or may not be the derived functors of the lim functor, and there may or may not be lim0. And please note that here we have a CW inclusion of something into something. And also please note that we have a very simple directed set. It's basically the natural numbers. What happens if we have a more complicated directed set? Well, there's a similar there's a similar theorem, but it's there's no. If we have a more complicated directed set, then everything gets more complicated. Because there's something which works for n and doesn't work for arbitrary directed set. Anyhow, so the gist is if you change, one should be careful with inverse limits. If you change something in this statement, there's a chance the result would be false. Now this this sequence can be found, for example, somewhere in Hatcher's book. I don't remember where exactly, but if you're interested, please send me an email, and I'll send you more precise information about where this can be found. Okay, well, let's okay. Well, let's we still. We still have a few minutes. Let's see which parts of well, let's see what we used in the Well, which properties of a multiplicative cohomology theory did we use in the proof? Well, we certainly did use two properties which I mentioned in the beginning. Now, well, the we also well, the proof was basically about comparing two long exact sequences. So we want to prove that we did use that. What did we use? There was a multiplication map from one long exact sequence to another one, and so we did use the fact that the long exact sequence is a sequence of modules over the cohomology of X. So we need the cohomology of every A and B, the cohomology of A mod B for every A containing B should be an H of X module 2, which it is because it's H of A module, it's an H of A module, but a slightly trickier thing is showing that the connecting homomorphism is a map of H of X modules 2. Did we use anything else? I don't think we used anything else, but if we did, then please let me know. And well, the last remark for today, it's important here that X is a space. If we have an arbitrary spectrum, then there is no natural ring structure on the cohomology of the spectrum with values in a multiplicative spectrum. So to get the ring structure, we need something from the target spectrum, yes, but also something from the source spectrum. And the source spectrum should be a co-ring spectrum, which is true for all suspension spectra, but false in general. Okay, we'll talk about it next time, because I want to do justice to this phenomenon. Are there any questions?